Hello students, welcome to Ahuja classes Smartness in Education. Today we are going to learn the next concept of fluid mechanics, that is the variation of pressure in a fluid when the fluid remains at rest. Before discussing the concept of variation of pressure in a fluid at rest, we must know the hydrostatic law, according to which the rate of increase of pressure in a vertically downward direction. When we talk about the variation of pressure or the rate of increase of pressure in the vertically downward direction in the fluid element is equal to the specific weight of the fluid at that point. So, variation of pressure refers to the concept when we move downward in the fluid, in the static fluid, then a variation in pressure is observed and that variation we have to measure. So, first of all, let us discuss the hydrostatic law. According to which the rate of increase of pressure in a vertically downward direction must be equal to the specific weight of the fluid at that point. And this law is applied when we have to measure the pressure at any point in the static fluid. It is used to measure the pressure at any point of the static fluid. To analyze this or to measure the variation of pressure in a static fluid, let us consider a smaller fluid element ABCD. In this element ABCD, let us consider let del A equals to cross sectional area of the element, let Z be the distance of Z be the distance of the element from the free surface of liquid, and del Z be the height of fluid element which we have considered, and let P be the pressure of fluid element on the face AB. Now, the forces which will act on this fluid element will be forces on the fluid element will be first pressure force P into del A on the face AB, which will act in the downward direction. Now, and the pressure force P plus del P upon del Z into del Z. Del P by del Z refers to the rate of variation of pressure in unit length, and on the del Z length the pressure varied will be del P by del Z multiplied by del Z into del A on the face CD. This pressure force will act on the upward direction, and next force which will act will be the weight of this fluid element itself. Weight of the fluid element W, which can be given by weight density or specific weight multiplied by volume. Weight density will be rho into G, and volume will be cross sectional area into height. Now here the cross sectional area is del A and height is del Z, so that weight of the fluid element will be rho G del A into del Z. There will be pressure forces on the faces AD and BC respectively, which will act in the horizontal direction. Since these forces will act in the horizontal direction, so that, and they are in opposite direction, so that they will be equal and opposite, so their resultant force will be 0. Now in the fourth force we have pressure forces on the face AD and BC which will be equal and hence resultant force in the horizontal direction will be 0. So there is no sense in resolving the forces in the horizontal direction. Now let us resolve the forces in the vertical direction. Now resolving the forces in the vertical direction. Let us draw the fluid element over here again, on which the forces are P into del A, which is being acted in the downward direction, and here we have P plus del P by del Z multiplied by del Z into del A, and we also have weight of the fluid element W as rho G del Z into del A, so that we will have, by taking the downward forces negative and the upward forces as positive, we will have P plus del P by del Z into del Z into del A minus P into del A minus rho G del Z multiplied by del A equal to 0. Now, opening the bracket, we obtain P into del A plus del P by del Z into del Z into del A minus P del A minus rho G del Z into del A equals to 0. These P into del A and P into del A has been cancelled out just because of the opposite sign, and by shifting the negative part in the rightward direction, we get equals to rho G del Z into del A, and this has been cancelled out. Del P by del Z equals to rho into Z. This is nothing but the hydrostatic law, according to which the left hand side represents the rate of variation of pressure along or with respect to height, and the right hand side represents the weight density or specific weight of the fluid element. We can write del P by del Z as small w, and small w represents the specific weight or weight density. Now, from this expression, as we have del P by del Z as rho into G, by shifting del Z in the rightward side, we get del P equals to rho into G into del Z. Now, by integrating both the sides, or if we take the complete derivatives, then we can write this equation as dP rho G into dz, and by integrating both the sides, we obtain P equals to rho G, and here it will be dz, and we will have rho G into Z. This is the pressure on a fluid element which is situated at height Z from the free surface of the liquid. So this is the pressure on the fluid element situated at height is Z from the free surface of the liquid. From here we can obtain Z as P upon rho into Z. and this expression represents the pressure head. So this is the analysis of the pressure variation in the fluid at rest, how the pressure varies from one point to another when we move downward in the static fluid. Thank you. In the next lectures, we will discuss about the next concept of fluid mechanics, but before that we will solve some numericals based upon the Pascal's law and the concept of pressure variation in a fluid at rest. Thank you.